The scale of the problem and the simulation setup. To understand fire behavior, the researchers built a virtual tunnel model that was 10 meters wide and 6 meters high. Each of the three sections, the main tunnel leading to the fire, the main tunnel continuing past it, and the side branch stretched 100 meters in length. The fire itself was a square, 2 meters by 2 meters, placed right at the crossroads where the tunnel splits. They tested 4 specific splitting angles: a relatively gentle 30-degree turn, a moderate 45-degree, a steeper 60-degree, and a harsh 90-degree right-angle split. To simulate different fire intensities, they varied the heat output across 6 levels: 5, 10, 15, 20, 25, and 30 megawatts. For context, a 5 megawatt fire is roughly equivalent to a few burning cars, while 30 megawatts represents a severe heavy goods vehicle fire. Before trusting the computer simulations, they validated the model against real-world physical experiments. The virtual results matched the real tests with an average error of just 9%, and even near the chaotic fire source, the maximum error was only 18%. They also verified that their computational grid was fine enough. For the largest 30 megawatt fire, the grid resolution ratio was 13.5, and for the smallest 5 megawatt fire, it was 6.7, both safely within the recommended range of 4 to 16, confirming the numbers were accurate. How the peak temperature soared. The most striking numeric finding involved the maximum temperature directly under the ceiling. As expected, increasing the fire's power raised the heat dramatically. Across all angles, the peak ceiling temperature rose from roughly 200 degrees Celsius at the 5 megawatt level to well over 1000 degrees Celsius at the 30 megawatt level. However, the bifurcation angle proved to be a powerful amplifier. For an identical 20 megawatt fire, the peak temperature was significantly higher when the junction was sharp. The researchers quantified this using an adjustment factor which they call K. For the gentlest 30-degree split, this factor was 6.81. When the angle increased to 45 degrees, it rose to 7.56. At 60 degrees, it dipped slightly to 7.20, and at the sharpest 90-degree junction, it peaked at 7.75. Although the 60-degree value was a tiny fluctuation, the overall upward trend was clear. Moving from a 30-degree split to a 90-degree split increased the adjustment factor by about 14%. They established that for every unit increase in the sine of the angle which measures sharpness, the peak temperature adjustment factor increases by roughly 1.92. In practical terms, this means a tunnel designer must expect a noticeably higher thermal spike right at the junction if the split is sharp, purely because the smoke slams into the wall and piles up. The surprising downstream cooling rates. While the peak temperatures were highest at sharp angles, the downstream behavior told a completely different numerical story. The researchers measured how quickly the temperature decayed or dropped off as smoke traveled away from the fire into the main continuation of the tunnel. For the initial rapid drop in temperature immediately after the fire, the decay rate at a gentle 30-degree angle was a high value of 2.24, meaning the heat crashed very quickly. But as the angle sharpened, this initial decay rate plummeted. At 45 degrees, it dropped to 1.99, at 60 degrees, it fell to 1.67, and at the sharp 90-degree junction, it bottomed out at just 1.40. This represents a staggering 37% decrease in the cooling rate. Why did this happen? The violent mixing at the sharp 90-degree junction introduced so much ambient air that the smoke was pre-cooled before it even entered the downstream section. Because this pre-cooled smoke lost its aggressive buoyancy, it slid along the ceiling with less turbulence, holding onto its remaining heat for a much longer distance. Consequently, although the peak at the junction was hotter, the heat hazard zone stretched substantially further down the tunnel in sharp angle designs. The upstream and branch tunnel numbers. Interestingly, the upstream section behind the fire showed a completely opposite trend. As the bifurcation angle grew sharper, the cooling rate upstream actually accelerated very slightly. For example, the coefficient controlling the slow, lingering decay upstream was a baseline of 0.073 at gentle angles, rising marginally to 0.089 at 90 degrees. This marginal 22% increase means that smoke trying to travel backward into the tunnel entrance cooled off faster when the junction was sharp, because the chaotic flow drew more cold replacement air from the entrance portal. The branch tunnel, the side split, followed the same pattern as the downstream main tunnel. The coefficient that governs how slowly the heat decays in the branch was 0.952 for the gentle 30-degree split. At 45 degrees, it held steady at 0.954, at 60 degrees, it was 0.948, but at the sharp 90-degree junction, it dropped significantly to 0.879. This drop of nearly 8% confirms that smoke entering the side branch from a sharp corner is already cooled and mixed, so its temperature declines much more gradually as it travels deeper into the side tunnel. Temporal stability and statistical confidence. To ensure the numbers were reliable, the simulation ran for a total of 300 seconds, 5 minutes of virtual fire time. The researchers did not use the chaotic initial moments, instead, they averaged the temperatures over the stable period from 200 seconds to 300 seconds. During this stable window, the temperature fluctuations were less than 3%, indicating a highly steady, reproducible state. Every statistical fit they produced came with exceptionally high confidence. The relationship between the bifurcation angle and the peak temperature adjustment factor had an R-squared value of 0.99, meaning the model explained 99% of the variation in the data. Similarly, the decay models for the upstream, downstream, and branch tunnels all boasted R-squared values between 0.96 and 0.97, confirming that the numeric patterns were extremely consistent and not random noise. Practical engineering ramifications. For a fire safety engineer, these numbers translate into concrete design rules. If a junction is designed with a sharp 90-degree angle, they must prepare for a peak temperature that is approximately 14% higher at the intersection than a gradual 30-degree design. This demands extra fireproofing material right at the corner to prevent concrete spalling. Conversely, because the downstream decay rate drops by up to 37% in sharp tunnel, the dangerously hot zone extends much further than standard straight tunnel formulas would predict. This means heat detectors, sprinkler heads, and structural reinforcements must be placed further apart or extended over a greater distance to cover the lingering thermal threat. Meanwhile, in the side branch, the nearly 8% lower cooling rate means evacuation routes and sensor placement must account for heat traveling deeper into the tributary than expected. In summary, the numbers from this study replace guesswork with precision, showing that a change from 30 to 90 degrees isn't just a geometric adjustment, it radically alters the thermal timeline, peak intensity, and spatial extent of fire hazards in the most complex parts of our underground cities.